assembly of whole genome reads. So let's have a small look into this topic. The genome assembly problem. And this slide I've taken from the course of Ben Langmead that I linked to in the document. And the assembly problem can be explained by making a puzzle where you have all the puzzle pieces, but you don't know how the final picture should look like. So, so we want from the reads that we have from sequencing a genome, we want now to assemble or actually put together these reads to make up the original genome sequence that we started out with before we cut it into pieces, right? And this, of course, is pretty difficult because we have many puzzle pieces. Many of them look quite similar to each other, and it's very difficult to know which piece should be in which part of the picture here, right? But this is what sequence assembly is all about. So we need to say a few words about graphs because this is a phrase that we need to deal with now. So this is a graph, a picture of a graph. And what is a graph? It's a way of organizing information, you could say. A graph consists of nodes or vertices. These are the dots here, and these typically are the objects that we store in a graph. We typically store in the nodes. And then we have edges between these nodes or vertices. That's the arrows here. And they indicate there is a relation between these two in some way. And I mean, the meaning behind an edge can vary a lot, right, in different graphs. We will see a couple of variants here now. But any edge indicates some kind of relatedness, whatever we mean by that, between nodes here. So we can see that these two nodes have something in common or should be linked in some way, but not these two, right? At least not directly. But you can see it's an indirect link between these two if you go, yeah. A multigraph is simply a graph with more than one edge between the node pairs. So there is no mystery behind it. I just mentioned it because this is a word that pops up in relation to assembly. Hamiltonian path. That's something that Ben Langmead talks about, I know, in his course. And that means a path is just a way of sort of walking through the graph, right? Following the edges. And in this case, if you have directed edges, as we say, it means you can only go from this node along the arrow up here, but you cannot go back again, right? Here you can go both ways because there is one arrow. And some graphs are directed and some are undirected, right? But we will talk about directed graphs. And then a Hamiltonian path means visit all nodes once and only once. So you can start somewhere, walk a certain path like this. This is a Hamiltonian path for this very small graph. Start here, walk it here, follow that arrow up here and that arrow out here. Then you have visited all nodes once and only once. In general, finding such a Hamiltonian path is really, really difficult if you have a big graph with lots of edges and lots of nodes. So this is one of the classical, you could say, difficult problems in mathematics and computer science, solving this Hamiltonian path problem. An Eulerian path is almost the same, but it's about crossing the edges. So now we don't worry about how often we visit the nodes, but each edge should be traversed once and only once. Right? It turns out that finding this is much, much simpler than finding the Hamiltonian path. And this is not really obvious unless you dive sort of deeply into the mathematics of this problem. But it tells us that if you're going to organize your data in graphs, it should be the Eulerian path you should be looking for instead of the Hamiltonian path in terms of easier to find, easier to solve problem, right? And this last problem here comes from a classical old problem you may have heard of, the bridges of Königsberg. And this is where the old mathematician Euler lived 200 years or more ago. And in this city there is a river, and there are 7 bridges crossing this river. You can see there's an island here in the river. And there was sort of a problem among the people in those days. They took a walk every Sunday, and they had sort of a competition if it was possible to start somewhere and go cross all bridges once and still come back to where you started. And you should only cross each bridge once, right? Not twice and not 0. And this was sort of competition among the people. But Euler, he actually proved this mathematically to be impossible. But finding this Eulerian path is sort of simple, right? If it's possible, right? It's not always possible, of course. But if it's possible, then finding it is not that difficult. And this is exactly what we are looking for when it comes to these De Bruijn graphs that we will see shortly. Finding the Eulerian path in the De Bruijn graph is actually solving the assembly problem. The first law of assembly is overlaps, has to do with overlaps. And it says that the longer overlaps we have between 2 reads, the more likely they originate from the same region of the genome. And this is pretty obvious, isn't it? I mean, you can have reads coming from wildly different parts of a genome, and still they can overlap a little bit, right? If the first read ends in, let's say, AAA, and the other read starts with AAA, they overlap in 3 letters. But that's very short overlap, and these can be from wildly different parts of the genome. But if they overlap with a very long subsequence, it's unlikely they come from different regions. They must come from the same region, right? And then we sort of glue them together, right? Long enough overlaps. So the assembly methods use these overlaps as a major source of information for sort of splicing together the reads, right? And I would say the natural or the first way to start approaching this is to make what we call an overlap graph. So now we make use of this graph organization again, and this was the first assembly softwares were made like this. Each node is a read, right? Because reads are sort of the objects we have, right? And we want to organize, how do we sort of organize the reads? Each node is a read. And then we draw edges between 2 nodes if these 2 reads, the 2 corresponding reads, overlap with a certain amount, right? It could be a sort of a lower threshold, so overlapping with 1 or 2 letters is not enough, right? You need a sort of substantial overlap. And then we can also put some information on these weights, so in sort of these edges. So you can actually sort of think of these arrows being thicker and thicker the more overlap you have. So here is an example of such an overlap graph. So each node here now, the circles here, corresponds to a read, right? And these reads are of different lengths and blah blah blah, but that's quite typical. And now you can see here we have made an arrow now between the 2 reads here, and this is because this read here, and you can see it drawn up here to the left, this read here overlaps quite a lot with this read here, because if we arrange them like this, in sort of align them like this, you can see that the last part of this read overlaps with the first part of this read. And the last part is what we call the suffix, the last n characters of a sequence. It's a suffix of that sequence. And this is the prefix, the first part of the sequence. Notice they are not identical because there is a position in the middle here where there is C in one and G in another. So in this case, we don't we don't require perfect overlap, right? Only near perfect, you could say, and it must be pretty long, right? A long overlapping region. Then we draw the arrow here. Now, making an overlap graph like this is very slow if you have many reads, because you really have to compare every read to all the other reads, right? In order to find if they must be sort of aligned, like we see here, right? So this is doable if you have a sort of a lowish number of reads, but as soon as you have million reads or even more, this is almost hopeless, right? Because it will take so long time to compare each read to all the others because there are so many of them. So this idea was a good one in the previous millennium, I would say, when we had few reads. Sequencing was a very slow process, and we only managed to make a few reads. Then this was fine, but with, for instance, Illumina sequencing, this is horrible. Theoretically it works, but it's only very, very slow. So, second law of coverage. The larger the coverage, the longer the overlaps will be. And this is not 100% true, but in general you can think in these terms. So what is the length of the overlaps then, given a read, read coverage D, and with some read lengths L? This is not so easy to. There is no sort of simple formula for answering this question here. You have to simulate, I think, in order to find it. But the larger the coverage, the longer the overlaps in general. But it has to. It will of course saturate. So going from super high read coverage to sort of a super high read coverage will not produce much longer overlap, because if you have high enough coverage, you could say, you already have very long overlaps. I mean, if the reads are 100 bases long, no overlaps can be more than 100 bases. and an overlap of 99 is what you need in order to sort of build the assembly, right? Or that's the longest one you can make use of. Having 100% overlap is no use, because then it's only a copy of the. You need reads who are not copies of each other, but overlap a lot. But having high enough coverage, we should say, is what we require. And going from super high to super high is no gain. The third law is about repeats, which is really the headache when it comes to sequence assembly. So a repeated region is a region of the genome that we find multiple times, right? And you should not confuse it with what we call low complexity regions, where we have a small set of symbols that are repeated over and over again inside the same element, right? Like this, T8. This is not what we call a repeated region. A repeated region is instead, think of it as a gene that has been duplicated. So you find the same gene on different places. And this will always create problems. So think of it here. For instance, we have a gene here, the yellow region here on the genome. This is the genome. I always draw them circular like this. And then you have a same gene in 3 different places. So when you have sequenced reads from this, so reads are now short pieces of this gene here, it's impossible to know if this read actually comes from this part of the genome or this part or this part, because they look exactly the same, right? These 3 yellow regions look exactly the same. And this causes problems. And a repeat is always relative to the read length. because if you have reads who are only 3 bases long, there will be many repeats, right? Because any sort of random, I mean, for instance, AAA will occur many times in a genome, right? That short regions are repeated all the time, you could say. But if you look at very long or longer regions, 3,000 bases, for instance, then you won't see many repeats because genes are in general shorter than this. So very few regions will be that long and at the same time repeated. Notice also that this problem with the repeats is not solved by having a larger coverage. There is no help. You can keep on sequencing till you are dead. It will not help. The only thing that helps here is to have longer reads. Because if the reads are shorter than the repeated regions, you are lost in a sense. You cannot resolve this, ever. Theoretically impossible. So the Bruijn graph idea. And Rod Edwards talked about this if you looked at the video, and I'm just briefly mentioning it here now. It's a spinning from this World War II encryption research, and you have probably seen this movie here. If you haven't, you should go and have a look at it. It's about the sort of the, what should I say, the dawn of computers, and Alan Turing, who was the man behind what we today call computers. So for an alphabet of size A, and for the DNA alphabet, it's 4, right? Construct all distinct k-mers. So all the different possible k-mers, right? This is sort of a theoretical exercise, right? Each node is then a k-mer in the graph, and there is a edge between the nodes if the k-1 suffix and the k-1 prefix of the other node is the same. So here we require absolute identical overlap. There is no mismatches tolerated here in this setting. So what does it mean in terms of read? In terms of reads. So first, collect all the reads. Collect all the k-mers from the reads for some choice of k, right? Some length. And then for each k-mer, collect the k-1 prefix and suffix. So if k, let's say k is equal to 4, then collect all the 3 mers, the first 3 letters and the last 3 letters in each 4-mer. And then we construct a graph where all the distinct k-1 mers are the nodes. And there is a new edge, and always directed edges in this case, because there is an ordering, right? What is before and what is after in a DNA sequence. So from node X to node I, if and only if, and this, I'm not sure if you are familiar with this way of expression, if with a double F should be pronounced if and only if. X is the prefix and Y is the suffix of the same k-mer. So let's see an example here what this means. Here I have a short read, right? From this read I now collect k-mers, and in this case k is 5, I can see, because this, so I collect one 5-mer here now, right? It's in the middle here somewhere, yeah. So actually you collect all, but let's look at only one of them. And then from this 5-mer I create the 4-mer suffix, sort of 4-mer prefix and the 4-mer suffix. And these two are now nodes in my De Bruijn graph. That's what I symbolize with the brown here. These are, now I started to build my De Bruijn graph. And you can see that these are the 4 first letters here, and these are the 4 last letters here. And then I draw an edge between them as an arrow, indicating that this one overlaps with this one in all except the first letter here or the last letter here. You can see that, ATG, right? and ATG. It's the same in both. They overlap. I collect another read, and from this read I also have some k-mers, and this is one of them. And now I can see that from this k-mer here, I notice that the first part of this k-mer is already in my De Bruijn graph. Can you see that? The first 4 letters here. So I don't add it again. I already have it in my De Bruijn graph, but what I add is the suffix, right? Because the last 4 letters here now also overlap with this one. So now I extended my De Bruijn graph with one more node. And so on. So you keep on collecting the reads, and from each read you collect the k-mers, and you look up, it's the prefix of the k-mer already in my graph. If it's there, then the suffix can be added, or it may also be there, of course. Then you do nothing. If it's already there, if both the prefix and suffix is already in the graph, then you have already sort of registered the information here. But in this way, this graph will now grow and grow and grow as you collect more and more reads and their k-mers. And notice that if we now sort of assemble together, if we start here and walk through the graph here now, then we know that we can build the sequence by starting with this one, and then since it overlaps with this one, we can just add the last letter to here. And since this overlaps with this one, we can just add the last letter here to here, right? So we can just add one new letter for each node we visit here now. So if this is a long line of nodes with arrows between them, then we are starting to build the long genome sequence. What we should notice here is that there is no really comparison between the reads. You never actually compare this read to this read. And remember, this was the big problem with the overlap graph, that you have to compare reads to each other. This is no longer needed. You only scan this read for its k-mers, and then you are done with this read, right? Then you scan the next read for its k-mers, and you are done with this one, and you never use it again, sort of. So you only run through the reads once, from one end, you could say, and you never compare pairs to each other. You just add the information into this graph, and then the information of this graph tells you everything you need to know about overlaps. So scan all the reads and build the graph. And that's much, much faster than comparing reads to each other. Overlaps between reads will appear as edges, yes. And only distinct k-mers are stored. So you never sort of, even if you see the same k-mer again, you never store it again. You add another edge. So if I see this one and then follow it by this one again, I just add one more arrow here. Or actually a number, right, on this arrow. This is actually the k-mer coverage. So if we look in terms of the overlap graph versus the De Bruijn graph, the overlap graph, that involves this comparison of all reads to all reads, which is horrible, right? However, there are some benefits. It gives quite a detailed information about overlaps, because overlaps can vary in length here, right? Some overlaps can be longer, some can be shorter, and this could be useful information. And also we tolerate mismatches here in overlaps. While the De Bruijn graph idea is much, much faster, especially when you have many reads, because you don't need to compare them to each other. Overlaps follow by the way the data are stored, right? So we have no sort of separate information about overlaps, but it's only the nodes who follow the nodes are indicating overlaps here. Of course, the prefix suffix must match without errors. So having a sequencing error will affect this way of building a graph very much. So it should perhaps not be a surprise that I already now say that this type of idea is very good for Illumina data, where we have large number of reads that we don't need to compare, but at the same time they are very precise, right? So we don't have a problem with all these mismatches. While if you have nanopore data, this idea is actually better in many ways, because we don't have that many reads anymore, right? They are few and long. So comparing reads to reads is not such a big job anymore, but the problem is we have a lot of mismatches, a lot of sequencing error. So we need to tolerate mismatches in order to find overlaps at all. Okay. So with many short reads and few errors, that's Illumina data. The Bruijn graph idea is the best, or has some benefits, right? That makes it this is most useful. But in terms of fewer longer reads with more errors, the overlap graph is perhaps a better approach. But you should keep in mind both approaches will work in both settings. Right? It's not like you only have to do one or the other. Both will work, but this one is fast, right? But this tolerates errors better. So it's possible to use both in both settings. It's just a matter of which one is a little bit better suited than the other. The repeat problem, yeah. So the repeats make k-mers non-unique, right? That's the problem. So when you do this in a De Bruijn graph, you will have bubbles, what we call, or you get more than one Eulerian path when you try to walk through the graph. Let's have an example here where we assemble in wrong order. So this is a De Bruijn graph now, and here it's not the DNA alphabet anymore. It's more like the ordinary alphabet, just to make it a little bit more visible, I think. And here we have now the 2 mares, right? So we have actually collected 3 mares. No, we haven't. We have collected 2 mares, and then we look at the, we have collected 3 mares, and then this is the k-1 mares, right? So you can see this 2 mare here overlaps with this one here, right? With one letter only then, because it's only 2 mares. And now you can see that after this AB, it overlaps both with BE up here. Yeah, it was not so easy to see, but it also overlaps with BC here, right? Because of the B. So when you are in this node, it's impossible to tell, should I now follow the red arrow here, or should I follow the green? It's impossible to say here, because it splits into 2 different Eulerian paths here. So if you follow, if you do the assembly in the first way, and then once you visit AB, you go on to BE. You follow the red path first, and then you just follow it around, and when you come back here, you just start on the second one, the green, right? And you add up like this, and you start with this one, then add the last letter here, add the last letter here, add the last, and so on. Then you end up with this sequence. But if you do it the reverse order, you follow the exact same graph, and instead of choosing the red path first, you choose the green path first, and then you add the red one in the second part, and then you have a completely different sequence. So this indicates that this repeated region, this here, AB, is obviously repeated. You can see it here. It's here and here in this solution, or if we are in this solution, it's here and then again here. So in both, we don't know which one of these two is the correct one, but we can see that in both cases the AB appears twice as a repeated region. So the only way to solve this is to have longer k-mers. Right? So if we could look at 3 letters at a time here, we would probably solve this, right? So with longer reads, we can also use larger k values, of course. I should also mention the importance of insert size. So remember, longer reads leads to fewer repeats. But when we do paired end sequencing, we have actually 2 rather short reads, but they span the same, they are from the same fragment, right? So the insert size or the fragment size is crucial here, because we know that even if the 2 reads are short, they must come from the same part of the genome, right? And they are separated by some bases. We don't know exactly how many, but this piece of information is quite important to make use of when you try to piece this together. So the spades that we will use this pairwise information, and all the assemblers that use paired end reads, they use this information. So if you have like 150 bases long reads, which is quite typical for Illumina, and you have an insert size of 750 bases, right? It means that you have fragments around this length, and then you sequence the first 150 and the last 150, and what is in between, the 450 in between, you never see. But you know they are from the same part of the genome, right? And using this information intelligently, we can actually handle repeats up to the size of the insert size. Even if the reads are much shorter, but because we know they are sort of linked together, we can actually resolve this long repeats. The sequencing error, this is of course something we have to battle with regardless of how you approach this. But in the Bruijn graph setting, all the substitution errors will cause what we call dead ends or subgraphs, or bubbles in the subgraph. So let me show you an example. Yeah, this may also be caused by other phenomena which is not relevant for microbial genomics. Diploid organisms, they are eukaryotes usually, really. But let's consider this here. So here I have a number of reads from the same region, more or less, right? So I have aligned them here. So let's just focus on this part here, which is aligned, right? So this region here is found in the end of, towards the end of some reads and in the beginning of other reads, right? But they all cover this region here. Let's keep this one outside at the beginning, with the red A in it. So let's only focus on the other 5. And they completely agree on how things should look like here in this window, right? So if we try to make the Bruijn graph, it looks like this. And here I use 3 mares, right? So CGG, the first 3 letters, is followed by GGT, the next 3 letters, right? And I have 5 arrows here because there are 5 reads that agree on this, right? And then we can just list all the 3 mares like this, and it continues in some way. But this is what we see inside this window. And then we have this read here. And of course, the first 3 mare here, GTC, is already in our De Bruijn graph. So it's here. But then the next one, TCA, it must appear as an alternative path here, right? So here we have a split like we saw previously. This is sort of the normal way, but this is an alternative approach, path, I mean. And then this goes on for a couple of k-mers, and then it goes perhaps back into the, yeah, I can see outside our window, it looks much like the other sequences here. And this is what we call a bubble in the graph, right? Where you have the, sort of the normal path, you can say, and then you have an alternative one that is sort of parallel in some region, and then it goes back into the normal path again. So these bubbles, they can be resolved to some degree by some heuristics in the software. You can even throw them away, and there is this option in spades you can set for throwing away. If you have many arrows here and only one arrow here, it indicates that this must be due to sequencing error, right? Because this is so normal that must be a. But this is not always the case, of course, right? We could have like 10 arrows here and 8 here, right? So it could be really a region that is repeated, right? That part of this region is repeated and it's found twice. This one will be repeated then, and it can be sort of extended in 2 different ways. The choice of the K, the length of the k-mers. So if we don't bother about running time or memory, which is usually something we have to bother about, but for now, let's not do it. The benefits of having a large k value, that's obvious, right? The larger k means fewer repeats. So why don't we choose k as big as possible? I mean, use the whole read as a k-mer. That's the biggest k you can have. Use the whole read, right? No. There are some drawbacks of large k value as well. First of all, this k-mer coverage shrinks if you increase the k value. And also, you have more effects on sequencing errors, because if you have very long k-mers, and if there are only a few errors, then very many more k-mers will have errors inside them, right? Because each k-mer covers a larger part of the read, right? So if a read has one error and you use very long k-mers, then almost all the k-mers have this error inside them somewhere. Remember this formula for the k-mer coverage, and you can see here if k is very big, close to L, then this fraction here becomes close to 0, and this one becomes much smaller than the read coverage. So you actually lose all the coverage information if you use a too large k-mer. In spades, the software spades that we are going to use in this course, they have sort of solved this by not choosing one k but a range of k values. So starting out with a small k value, try to assemble as good as you can, and then when you're done with that, you start all over again with a slightly bigger k value, but then you also make use of the results from the first round to try to improve, and then choose gradually increasing k values. And this of course makes it slow. So making an assembly with this software here takes some time, but it's also considered to be sort of the best precision you can get in using short read data. Contigs. There will always be some parts of the graph that we cannot resolve. It's not like everything is overlapping with everything, or the graph will not give us the whole genome from start to end. And the practical solution to this is just to give up. Split the graph into several subgraphs and then reconstruct one piece for each subgraph. And that's what we call the contigs. And this is what we end up with after sequence assembly. You don't end up with the whole genome. You cannot make the full puzzle, but you can make parts of it. Some are pretty big, and then you are really happy. But some of them will also be quite small, the difficult parts, you could say. We will see this. And the contigs are not really possible to order to give them an ordering. We never know which contigs is upstream or downstream of the other contigs, really. In some few cases we can make what we call scaffolds, by using this, yeah, usually it requires some extra sequencing, but it may be reconstructed from how the from paired end reads, right? That contig B follows contig A, but we don't know really how the gap looks like, or not even exactly how long it is. And then we can fill in some ends in the gap there, and in that way sort of artificially glue these two contigs together into what we call a scaffold. But this is not really, in reality, we are happy with these contigs, right? Let's have a look at the output we get from Quast. So here I have this Quast spades folder that has been filled now with output from the Quast software. So let's click into this one and have a look at this report here. So you just click and view in browser, and it should look something like this, depending on the size of your window. And first of all, we used a reference genome when we evaluated our contigs here. So I think the very first thing I would look at here is this, the genome fraction in percent. What is this? It's an estimate of how much of the reference genome is covered by our contigs. So the contigs are aligned to the genome sequence. It doesn't have to match exactly, but there are some alignment behind this, right? So if you want to dig into the details here, you can put your mouse over like this and read this text that appears. But basically this tells us how close we are to reconstructing the genome, right? Especially in this case, since the reference genome is actually the genome that we sequenced. So ideally here it should be 100%. And the reason it's not, it's because sequencing errors and problems with short reads makes this problematic. So there are some other statistics here. I will not mention any of them almost, but in the extended report, if you click on this one, you can get much more information. And here we find, if we scroll down, the N50 that we talked about. The N50 is 326,113. So this is a length of a contig, right? This is a length of a contig. And this should be as large as possible. The larger, the better. And we will have a look at what is actually this N50 now. I click it down again. Let's have a look at this plot here, because this explains this really. So first of all, here we have in this figure now the cumulative length, it says. And if I click away the spades, the red curve, you only have this this broken line here, and this is the reference, right? So if you sort the reference sequences with the longest one first in decreasing order, right? Then you have one very long sequence here, which is 5.4 million, right? Bases long, and this is the chromosome. This particular genome also has one extra. If I move over here, you can see it's sort of the second contig. It says it's not really contigs, right? Because these are actually genomic sequences. But this particular reference genome has a plasmid. It has a small plasmid, so you can see the chromosome is 5.411,000 blah blah, and then if we skip here, it's 5. If we add the plasmid, then it's 5,427,000. So there are a few thousand extra bases in this plasmid, right? And then it's flat. So this is the length of the genome. So if we now add the contigs, these are also cumulated here now. So the first contig is up here, is more than 1 million bases long. So that's our best config, I would say, right? This is the best config, the longest one. And then we jump to the next config here. And then the sum has increased to 1.6 million. So the second one was like 500,000 more. And then we jump to the third config and so on. And this accumulates, right? The length of the configs, less and less now because it has been sorted with the longest config first. And we can see that when we come up here, it sort of flattens out a lot because now we have all the sort of bigger configs and the rest here now is only tiny small rubbish configs, I would say. And we reach 98% or something. 98.75, which is very good, I would say, right? We almost reconstruct the whole genome, but there is something lacking here. This N50, if we click on this one, NX tab, you can see there are multiple sort of tabs over this plot here. So here we can actually also see the N50. And let me explain. So here we start now with the first config, right? And when we include one config, we have covered almost 20% of the genome, right? That's 19.56 it says there. And there you can see it better, right? And then if we include the two longest configs, we cover 30% of the genome. And the three longest configs, we are almost 40%. Four longest, now we are closing in on 50%, which is the magical threshold here, 50. And here we have it. The fifth config, then we go beyond 50%. Now we are up to 52. So now we have covered more than half. And now the length of this config is the N50. You can see here, 326,000. Right? So remember this, it's the length of this particular config where you cross the 50% sort of barrier. And if you wanted to compute N75, meaning that it's the length of the config where we pass 75%, and that's here, isn't it? Yeah, there it's 73, and if we jump up there, it's 77. Now we passed 75 here. So the length of this config will be our N75, 189,000. And so on. N90, for instance, is here. The length of this one. Okay. One more thing. The misassemblies that is mentioned here. There is one misassembly. And what is a misassembly? Let me show you this PowerPoint slides here to explain what is meant by misassemblies in Quast. So imagine we have a config here, right? And it's now colored. The first part of it is sort of yellow and the last part of it is green. But this is a whole config, right? One single config. Here we have the reference genome. It's actually two, and because this is also applies to metagenome sequencing, which is something we will look at later. But for now, we forget about the second one here. We only consider one chromosome, right? This could be the plasmid though, but that's super small, the plasmid. So we have a reference genome. And then misassemblies look like this. There are sort of three types of them. Relocation, if first part of the config matches the reference here, and then the last part of the config matches over here, and there is more than 1,000 bases in between here, then Quast says this is a misassembly. This config, there should have been something more inside here, right? This config is wrong by relocation, it says. And this threshold of 1,000 base pair, of course, this is something you can adjust, right? So this is just set by default here in this software. Another way of making a config wrong is this inversion. And then we can see that they actually sort of matches, but this matches on the other on the other strand, right? So we have, if we use the sort of positive direction on the chromosome, it looks like we are on the positive strand here and on the negative strand here in this config. So this is also considered an error, right? This one should have been flipped, or actually this one, one of them. The last one here is if part of the config matches one chromosome and another part matches another chromosome, and this cannot really happen in the single genome data, right? If this was a plasmid, it could happen, right? If we have a reference with a plasmid. But this is something that more typically happens when you have metagenome data. We will come back to that, where you have many different genomes. So we actually make contigs who are mosaics of two different genomes. But the two first ones can easily happen also for single genome sequencing, right? So we can see, if we go back here, there's one misassembly here, and it's in this config here with this length. And I mean, it's misassemblies like this will happen frequently, I would say. It's not something that you see a lot of, but you rarely see none of them. One or two or three, five usually occurs. So sequence assembly is by no means perfect, even if it's not that far away though, almost 100%.